how do neural nets learn? In fact, what does it even mean for a neural net to learn? Hey y'all, my name is Jonas Cleveland and I am a host of Building.ai. I'm building this channel for the aspiring entrepreneur and investor who wants to create a better world using technology. We are going to be covering everything generative AI, everything Web3, and everything sustainable energy. You shouldn't invest in something if you don't have at least some high-level understanding of how it works. So on this channel, we're going to be taking a deep dive into how each of these technologies work so that we can understand the difference between the hype, oh, you know there's some hype out there, y'all, and the real, actual business opportunities that exist. My goal is that this will be the fastest lesson on backpropagation on YouTube. Drop in the comments your thoughts and any links to other resources also. By the end of this video, you're going to understand how backpropagation and gradient descent work together. My goal is to take what others spend a few hours explaining and make it much more simple, condensing it to 10 to 15 minutes.
Hey there, I'm a cute little kitten. Jonas put so much work into these videos. Like and subscribe, please. Like it. Wow.
At the time, Pablo owned half the police in Medellin. But DOS was Colombia's version of the FBI. They didn't play by the same rules.
Gradient descent and backpropagation are the algorithms that work together to teach neural nets. Even experts in the field struggle to understand exactly how these algorithms accomplish what they do.
And I've actually used backpropagation, pretty successfully for many years, and even today I still don't sometimes feel like I have a very good sense of just what it's doing.
In order to train our neural nets, of course we could tweak all the weights randomly and observe which weights work the best, but that would suck, especially when there's often hundreds, thousands, or millions of neurons in our neural net. There are several optimization algorithms, but the most popular method is to use backpropagation along with what's called stochastic gradient descent to teach our neural nets how to learn. Now, I do want to preface this by saying that in today's world, most of this backpropagation and gradient descent is practically taken care of by frameworks such as Keras and PyTorch. But it's important to understand the fundamentals of these algorithms if we really want to optimize performance and also custom design our networks. The motivation of this approach is to reduce the error of the neural net function. Now, although these two algorithms are often talked about in tandem and almost interchangeably, there's a lot of confusion about how they actually work separately and in cooperation. So to be clear, backpropagation is defined as the process of actually computing a formula. And the formula that we're computing is for our specific neural net. And the formula is the gradient of the neural net with respect to the loss or error. So in backpropagation, it is taking the derivative of the neural net with respect to the loss function. And then, once we have this formula, we will run gradient descent to find the minimum of the derivative with respect to the loss function. Gradient descent is the process of using the formula that we get from backpropagation. Let's pause here for a moment to grasp the intuition. The neural net is composed of many neurons, and each is its own function. A number of inputs map to the neuron, and the neuron multiplies each of those inputs by a weight, and the result of the multiplication and the sum, or the dot product, is the neuron's output activation. So, if we can find the rate of change of the neuron's weights with respect to the neural net's error, then we can find the weight values that reduce error. Okay, so we know from calculus that we can take a derivative of a function to find its gradient, or its rate of change with respect to the input value. If we understand how much the function output changes based on its parameters or weights, with respect to the loss, or with respect to the error, then we can work to find the parameters or weight values that work best to reduce the loss. Let's take a look at a formula for an output neuron for the sample neural net. We see there are two parameters here, the weights and the activations, which we originally got from the input. Since we want to find the error or loss function with respect to the weights, we need to hold the activations at some unchanging value. So we choose one training example in order to keep the activations constant. And then we compute the formula for the gradient of the neural net respect to the error. Once we have this formula, we will then run gradient descent to find the minimum of the derivative. So our goal with backpropagation and gradient descent is to be able to reduce the cost with respect to our weights. So we want to modify our weights to reduce our error. So this is what the cost function will look like. Okay, this is what the cost function will look like for one weight, and for two weights it would be three-dimensional, and very quickly we run out of a convenient way to be able to visually show this, but this is a convenient way for us to see or visualize and think about what we're doing with backpropagation. We are first finding this formula for the error with respect to the weights, and then we're going to find the lowest points, the local minimum for our weights. So this is our sample feed-forward neural net, and this is the same feed-forward neural net, by the way, that we used in our feed-forward neural net video. And we can see that from this neural net, we're able to get these formulas. These are the functions corresponding to our neural net. Our cost, and we're using the mean squared error, so that's just the activation minus the output squared. Zeta, it's the output weight times activation plus bias, right, for each layer, and the activation, which is zeta wrapped in sigmoid. Now, what it turns out we're going to do is we are going to take the derivatives of these formula, and then we're going to use the partial derivative for the chain rule to find the derivative of the cost with respect to the weights. So we are going to take the partial derivatives of these functions and then use the chain rule to be able to determine the derivative of the cost with respect to the derivative of the weights. When we take derivatives, the partial derivatives of these formulas, this is what it looks like. The derivative of the cost with respect to activation, 2 alpha minus y, sigmoid wrapping zeta, and then the activation at each layer. And by the way, we do remember that the sigmoid function is simply the ReLU that's wrapping our activation. And the ReLU is given by this formula, as a quick reminder. Now, this is the formula that we have for our neural net example, and this is a closer look at our sample neural net. And again, we are now going to be using the partial derivatives for each of these terms to determine the derivative of the cost with respect to the weights. Now, if we were to perform a derivative chain for the highlighted sections in our neural net, this is the way that the terms would look. And what you can see here is that going from right to left, we're working from the output to the input layer. And similarly, for a path that looks like this in our neural net, this would be the chain, the partial derivative chain that corresponds. So when we combine the previous with this current chain, it gives us the total expression for the cost with respect to W11. Now, once you've gone through all of your layers and you have all of your partial derivative chains, congratulations, you have completed backpropagation. And now it's time for us to move on to gradient descent. So let's go back to the algorithm. Again, backpropagation gradient descent consists of 3 primary steps. For the positive training example, perform forward propagation, compute the derivative gradient of all the weights with respect to the loss function. Okay, we did that. And then moving backwards across layers, compute the gradient of the neurons at each layer. We've now done that. So now we're going to perform gradient descent on the weights for this particular training example. You will recall that gradient descent is the process of finding the local minimum of a function. Because we know that the minimum of a function corresponds with its slope being 0, we found the gradients of neuron functions in the neural net. And we have found those gradients with respect to the weights of the neural net because the weights are the parameters that we are modifying. So now for each neuron, we are going to modify the weight iteratively according to the formula, where delta sigma is the step that we take walking along the gradient. So now for each neuron, we are going to modify the weight iteratively according to the formula Wi equals Wi plus delta Wi, where delta Wi is mu, or the learning rate, times the change, the derivative of the weight. So in this way, we're basically tweaking the weight, modifying it slightly. We're going to set how much we modify it in each iteration by a parameter called mu. And following this step, right, you can see that as we get to a local minimum, the change is going to equal itself. It's going to converge. And that's when we stop gradient descent for that particular weight. And that's when the gradient descent process completes for that particular weight. And we're going to do this for all weights in the neural net. So guess what? That's it, y'all. Now you know how gradient descent and backpropagation work to teach neural nets. You might have to watch this video several times before you grasp all the concepts. And that's okay. By the way, the beauty of these algorithms is that since these are all vectors, they can be parallelized. We can leverage the power of GPUs. Speaking of which, ever wonder how GPUs emerged, like why they were originally invented and why they're so important to the continual advancement in AI? All right, well, we're going to create a video on that. My name is Jonas. I built this channel that you can learn about the underlying concepts in generative AI. Like and subscribe, and until next time.